So remember that we need the first four assumptions to be satisfied to prove the unbiasedness of our OLS estimators. Okay, which is basically saying that the expected value of beta hat j, which is, the slope coefficient associated with the variable, the independent variable xj, equals beta j. So the difference between your beta hat and beta is that when we talk about beta hat, these are our estimates, right? This is coming from, or this is an estimator. This is coming from the random sample that we've drawn from a population. And this is what the population parameter is. Okay. Now remember that if you included an irrelevant variable or you overspecified the model in some way, that is not going to cause any bias in the coefficients. So that's not a problem. If you had some extra arguments or you threw in some extra variables, that is not a problem. However, if you left out a variable that was important and should have been included in your model, that becomes a serious problem, and in which case your model becomes underspecified, or in fact, we call that model misspecified. So you want to make sure that you've sort of thought about all of the variables that might influence or affect y. Now we've talked about the bias, so I'm not going to go over this. You can look into this, but basically if you went from a simple linear regression model to a multiple linear regression model, we can always think about the bias in the simple linear regression case of that slope coefficient. Okay, and this is the bias when you have two explanatory variables in the multiple linear regression case. Okay, so since we know what the bias is, we're saying beta 2 times delta 1 hat is the bias of beta 1 tilde. We can at least think about two scenarios. One scenario is if beta 2 is equal to 0. So maybe it is the case that in the population, the effect that x2 has on y is just 0. Okay, so which would basically tell us that, okay, we're fine with the simple linear regression. We don't really need the multiple linear regression. The other thing that could happen is that the correlation between x1 and x2 is 0, which is going to make this delta 1 tilde equal 0. Okay, so remember what delta 1 tilde was. It was basically the regression of x2 on x1. So the way we were deriving delta 1 tilde was basically running the regression of x2 on x1. Okay, so if these two hold or either of those hold, then the bias disappears. Okay, and in the simple linear regression case, the estimator becomes unbiased. In other words, the expected value of beta 1 tilde will equal beta 1. Now, you can take this further and try to assess, looking at this really neat table, in which cases the bias would be positive or negative. So here you just have, values given for your, so remember bias equals beta 2 times delta 1 tilde. So delta 1 tilde is basically going to capture the correlation between x1 and x2. So here it's showing you that, let's say, beta 2 is greater than 0, and the correlation between x1 and x2 is also greater than 0, then the product is going to be positive, and so it's going to cause a positive bias. Okay, so you can see how the whole table makes sense. So basically, depending on the sign of each of these, you're going to say if the bias is positive or negative. And this is the bias in the slope coefficient of your simple linear regression, remember. So y equals so we're talking about the bias in this slope coefficient. Now, just to kind of tell you that once we include more and more variables, determining bias becomes more difficult. Okay, so when you have more than 2 explanatory variables, this becomes difficult. But at least you want to give it a thought. Okay, so just to recap, you need the first four assumptions to prove unbiasedness. And in the next video, we will talk about the variance of our estimators.